Yeah. So the last talk is about quantum programming. So Nicola is giving the talk.
Yes. Hi to everyone. I'm Nicola Assolini, and in this talk, I will speak about static analysis that is built for detective entanglement inside of quantum program. So we are speaking about quantum. So, all right, doesn't work. Right. Okay, now it's working. All right. So, okay. So let's start from the beginning. In quantum computing, we are working with the smallest information unit is the qubit, different from the classical world. So from a mathematical point of view, a qubit can be represented with a vector in a two-dimensional Hilbert space. Thus, to represent a qubit, we need two bases, since you're in a two-dimensional Hilbert space, that usually are 0 and 1, that correspond to the classical value 0 and 1 of the bit. Then we will have two complex coefficients, since an Hilbert space is a complex vector space. And a value of the qubit will be a linear combination of these two base values. And here we see the main difference with the classical computation, since the value of a qubit is a linear combination, or as the physics say, a superposition between the two values. This means that a qubit is not only 0 or 1, but can be both 0 and 1 together, with some amplitude that are indicated with the complex coefficient. So we are talking about entanglement, so we need to consider system in which we are more than one qubit. For example, let's consider a two-qubit system. When we put together two qubits, first of all, we need to build this vector space of these two qubits. How we build it? We build it putting together the vector space of the single qubit using this operator that is a tensor product. So in this case, since we are combining two bidimensional Hilbert space, we will get a four-dimensional Hilbert space. So we will have four bases that are basically the combination of the two bases. And the state of a two-qubit system, it will be a superposition of these four bases. In case we have three qubits, we will have 8-dimensional, so 8 bases, and so on. Thus, we have seen that when we are putting together qubits, we can obtain the vector space of the qubit using the tensor product. So there is one question that arises, is since the vector space can be obtained in putting together the single vector space, is a state of two qubits the result of a combination of the single state of the qubit? The answer is sometimes. In particular, when we can write a two-qubit state as a combination of the single qubit, this means that the two qubits are separable. So we have two independent states, and the state of the global system, it will be simply the combination of these two independent states, like in classical computing or probabilistic computing. Instead, when we cannot write a state of two qubits as a combination of two single states, it means that these two qubits are linked together, and their state cannot be described considering one qubit only, but we need to consider these two qubits together. And this happens when the two qubits are entangled. So when two qubits are entangled, basically, we have multiple qubits that correspond to a single state that cannot be broken. We can see an example. For example, if you have like this state that is a superposition of all the four bases, we can write it in this way. So in this case, Q0 and Q1 are separable. And you see that we have Q0 that is a uniform superposition between 0 and 1, and Q1 that is 0 plus 1. So in this case, they are independent. Instead, we can have a state like this one, in which we cannot separate the state of the single qubit, because you see that the first qubit is 0 only when the second is 0. Similar with 1, the second qubit is 1 only when the first one is 1. So it means that the state of one qubit depends also to the state of the other one. And like in this case, we have that Q0 and Q1 are entangled. This the entanglement property is a powerful property. It is used in a lot of algorithms, but can cause also some problem because, for example, if in this state we decide to measure the first qubit, so we do an operation only to the first qubit, here you see that the first qubit is 0 plus 1, so the measurement will give us two results. The measure it's a probabilistic operation, so we'll have a different result. In particular, we can have that the first qubit is measured as 0 or measured as 1. But since the two qubits are entangled, if after the measure, the result of the measurement on Q0 is 0, we are basically here. It means that the second qubit will be 0. No more superposition of value. Similarly with 1, if we measure 1, we are here, and also the second will be 1. So you see that where we are working with entangled state, if we work on one qubit, we are also changing the state of all the other qubits that are entangled with that one. For this reason, inside of quantum programming language, it's important to understand which is the entanglement relation, because we may have some operation, some variable that are also altering other variables that we don't know. And this is the aim of this analysis, understanding which are the entangled, approximating the entangled relation between a variable inside the program. So before introducing the analysis, let's introduce the language that we have used to define the analysis. We are using this regular expression language that is useful because it has a really simple syntax. You see that we have the first command that corresponds, that also the other nice things of this language is that this language directly corresponds to a control flow graph. In particular, we have three constructs. We have the sequential composition, the branching, and the iteration. And then we have the label that correspond to the label that we put on the edge on the control flow graph that are the statement of the language. In particular, we consider two special statements that are measurement 1 and measurement 0 that are useful for building conditional statement. For example, with the if then else, we can build the usual if then else that there is in quantum programming languages. That is an if then else in which we have a quantum guard, and according to the result of the measurement of Q, we choose C1 of C2. We see that in this case, we can write this statement using our syntax in this way. So we have a branching, and we say if the measurement of Q return 1, do C1. If the measurement of Q return 0, do C2. Then we have the three quantum statement. We consider only these three simple operations because in quantum computing, using only these three gates, we can model every possible quantum computation. So it's useful for defining the analysis. In particular, the operations that we are considering are the Hadamard gate. It is like the most quantum gate in quantum computing because it's the gate that creates superposition. So if you have 0, it creates 0 plus 1. If you have 1, it creates 0 minus 1. Then we have the T gate, that is a rotation, and it applies a rotation of pi divided by 4 to the second part of the state. And then we have the control knot, that is a control knot. So we negate the second qubit if the first one is 1. You see on this example, we have a 0, 0, 1, 0. After the C naught, we will have 0, 0 because the first one is 0, so we do nothing. And then here, the first one is 1, so the second one became 1. And we see that the C naught is also the gate that introduces entanglement, like in this example. So the second ingredient of our analysis is the abstract domain that we use to represent entanglement. In particular, with this abstract domain, we want to achieve two goals. We want to represent the entanglement relation between qubits, and also we want to try to approximate the value of the qubit during a computation. So let's start from the first task. The most naive way to represent an entanglement is if you have a state like this one, in which we have two entangled, in which we have A and B that are entangled together, and C and D that are entangled together, and A and C and B and D that are not entangled because we can separate the state in two. The most naive way to represent this entanglement relation is considering the set of the variables, so A, B, C, D, and using a partition of this set. So we can use two sets. This set say that A and B are entangled together. This set says C and D are entangled. Since C and B, for example, are not in the same set, it means that we can separate the state here. However, using only this representation is not enough because, as we see in this example, if we consider the two parts of this state, and we decide to apply a control knot operation to both this part, you see that in the first case, if you apply a control knot operation between A and B, so we act on this part of the state, After the control knot operation, we will obtain this state that is still an entangled state. Instead, if we look to the second part of the state, and we decide to apply a control knot operation between C and D, you see that after the control knot, we obtain this state in which D is no more entangled with C. So this means that the relation between C and D and the relation between A and B are different because they are both entanglement, but like the level of entanglement is different. And in particular, we are interested in tracking this kind of relation because when two variables are related like C and D, with a simple C knot, we can separate them.
When you say abstract domain, in fact, this is in the concrete.
Yeah, I mean, yes, this is in the concrete, yes. This would be the abstract, and then we are building the abstract. Yes, I mean, this happened in the concrete, yes. And we want to represent what happened with this particular feature in the concrete in the abstract domain. So what we want to represent is basically when there are this relationship, this kind of relationship, that we call C-not separable in this presentation. So here, graphically in this presentation, we represent this relation using a line. So in our abstract domain, it will become a partition of the set of the variable plus this additional operation that say these two variables are C-not separable. So in our analysis, we know that when there are this relation, with a C-not, we can break the entanglement. Then the other,
question.
Yes?
Do you just do this for C-not? Because I could hit it with a Hadamard then.
Yes, yes. No, in this work, we do only this with the C-not. Okay. We plan like to try to improve the representation because in a more complex level. And there is an example after that show also the loss of precision. But yeah, we consider only the C-not for now. And okay, the other goal of our presentation, of our domain is to represent try to approximate the value of the qubit. So let's see a couple of examples that show which are actually the value that we need to represent. Let's start for this one. You see that if we have a state in which the first qubit, the controller in this case, is a classical value, since the controller is classical, the control knot will be the same as a classical control knot operation, and thus we don't introduce entanglement. Then there is another case in which we have the controller that is a quantum state, but the target is this particular state, that is the state in which we have a uniform superposition between 0 and 1. And when the target is in this particular state, you see that the C-not basically is equal to the identity. So also in this case, we don't introduce entanglement in the C-not. And then we have this final example in which we have the target, the controller that is a quantum value, and the target that is a classical value. In this case, the C-not introduced the entanglement and also created that particular relation to have seen before. So in our domain, we are interested to tracking where the qubits are in classical value and also in uniform superposition. How we try to do this? We introduce some label. First of all, we introduce a label that corresponds to all possible classical value and a label that corresponds to all value in which we have a uniform superposition between two bases. So this counted also 0 plus 1, for example, but also 0, 0 plus 1, 1, and so on. So we will have a lattice like this one, the two labels top and bottom. However, in our language, we have the T-gate. And if we try to represent the semantic of the T-gate on this lattice, we obtain this. We have with the classical label that is OK. But if we apply the T-gate to the set of value in this label, we go directly to the top. And of course, this is not nice. So to improve the precision of the T, we can add other tree label, because the T has this interesting behavior in which if we apply T 4 times to a value in the X label, we come back again to the X label. Quindi simply adding other tree label, we are able to represent the T in a more precise way. Then we also add this other label S, because we are interested when we do a join between one of these 4 labels, we obtain a state in which we always have a superposition between two bases. You see that the only difference between these 4, is the phase, but we always have B plus minus B, the negation of B. So we introduce also S, that is every state in which we have a uniform position between two bases, and then we have the top and the bottom of the lattice. So how we put together the label with the domain in the abstract domain. As we have seen before, when two qubits are entangled, there is no meaning in describing the state of the qubits separately, but their state corresponds to a unique state. So we decide to associate a label to each set of entangled qubits. In particular, in our example, we have, let's recall the label, we have this state that unfortunately does not correspond to none of this label because we have a superposition of 4 bases. So we label this at top. Instead, in the second case, we have a uniform superposition between 2 bases that correspond to the X label. So we can label it at X. And this is the representation of the state in the abstract domain. Let's see how we use it on a simple program. We consider this program, which there is no control flow graph, as simply a sequence of operation. So we start from, we can assume that at the beginning of the program, all the qubits are in the 0 state. This is a normal assumption in quantum computing. So in our abstract domain, we will start from a state like this one, in which we have all the 3 qubits that are separable and classical. Then we do the Hadamard gate to the first one. So we change the label to the first one, to classical, to uniform superposition. Then we do the first CNOT, that is a CNOT between a quantum value and a value that is classical. So the relation is to become a CNOT separable relation, and the semantic of the abstract semantic of the CNOT give to the pair the label of the target, of the controller. So since the controller is X, when we do the control node between a quantum value and a classical value, we obtain this relation with the label of the controller. The same happens with the third CNOT, since the controller is a label X, in particular is A. The target is classical, so we will have this relation. You see that it corresponds to this, in which we have a uniform superposition between 2 bases. Then we do a CNOT between 2 values that are CNOT separable. So of course, we delete the entanglement. So what happens? The target, it becomes a classical value, and it is no more entangled with the rest of the qubit. How it happens here. Here, now we decide to apply an Hadamard to A. And here we see where we lost precision. In fact, since we apply an Hadamard to A, we pass to this state to this other state. So we are not more in a state in which the qubits are CNOT separable, and it's no more a state that are related to some label. So unfortunately, we have to remove this line and to change the label as top. So basically, what we have here with ASC, that the value of ASC is basically the top of the lattice, because we consider them entangled. Since we want to approximate, give an over approximation of the entanglement, here they are entangled, so there is no more information. Basically, this corresponds to no information about A and C, and the label is top. In fact, if at this point in the program we decide to do these 2 operations that nullify the entanglement, okay? If you apply this operation to the abstract domain, since basically this part of the test does not contain no more information, because we say simply entangled, we don't know the state, they remain entangled. So here we see that is connected to your question before. We see that where there is the loss of precision, because for now we are able only to represent this kind of relation. And okay, so in conclusion, we have introduced this static analysis. The goal of this static analysis was to improve the state of the art. In fact, in the state of the art, there was only this kind of representation, considering the qubit together without trying to represent the entanglement relation between entangled qubit. So what we have done is to introduce this CNOT separable relationship that allows us, in some situation like this one, to separate the qubit. However, we have seen that this is not enough, since the entanglements are a really complex phenomenon. In fact, as future work, we aim to try to improve the representation, so getting more in a direction in which we have a more complex representation of the entanglement, and also try to test and implement this analysis considering a more complex language with more gates, and also to give like a use case and some testing with real languages. And thank you for the attention.
So I wonder why you just focused on C naught. So for example, you could have handled the Hadamard by saying, if I apply Hadamard twice, that's identity, right? So you could have expanded your domain. Why did you choose to stop here?
We choose to stop here because these ones, because like for example with the Hadamard, because this relationship can be defined using, I have like an example here. This relationship can be defined using the measurement. In fact, yeah, when we have like the C not separable property, you can define the states that are in this property, checking what happens when you do a measurement. In fact, when you have like the C not separable property, it happens that if you measure one qubit, the other that are C not separable with them collapse directly to a classical state. That don't happen in a general quantum state, in general entangled state. So like this property was like the property that was that we managed to define it in a sound way. For this reason, we only consider C naught, because with other gate, like with Hadamard, for example, you can say this is a C naught Hadamard separable, but it's like listing the gate and then try to coming back. So this was the reason. In fact,
do you know the exact complexity of this problem? I mean, if you didn't want to solve it with
I mean, classifying entanglement state is NP hard with a lot of them, and yes.
Can you extend your approach to support, for example, Toffoli gate control not?
Yes. Okay, yeah, like in this work we consider, like also for giving a more clear definition, we consider only that tree operation, but in general, like you can extend the approach, but you only have to define the abstract semantics, considering a different gate. So yeah. With Toffoli gate, it probably will be more difficult to. There's some feedback. It will be some problem probably to catching when you create a C not separable gate, because you can have like it's depend. I mean, you have more cases because since you have two controllers, you can have one controller that is quantum, the other is classical, both are quantum. So probably you may find the more difficult, more problem is trying to get the C not separable property. So that is the main problem. So, yeah. But in general, you can.
More questions? Actually, I have one, because this is all new to me, so I want to go back all the way to your motivation.
Yes.
And I was trying to understand why analysis of entanglement is important.
Okay, the main reason is the first example. Because, okay, let's go in the presentation.
I mean, I know what entanglement is.
Yes.
I'm just trying to understand why.
Yeah, this basically explains it. Okay. Because basically, here we see that when we have entanglement, if we measure one qubit, and this also and this also happens with other operation. For example, if you change the relative phase of the first one, you also change the other one. So, like first of all, it's important because if you want to analyze, in general, you want to know like which operation on which variable you are working on. It's not like in the classical case in which if I write measure Q0, I'm not only working on Q0. And this is related also to another problem which in quantum computing, if you want to like drop a variable, like remove a variable from the memory, this corresponds to a measurement. So you not always can do it safely, and knowing which are the variable entangled with a particular variable can give you an information to know, like if I measure this variable, because basically a measurement broke something in the state, so you know also which are the variable effective of this operation. And in general with all the operations.
So in your program, it might look like you're only measuring Q0.
Yeah, exactly.
Actually, you're
yes.
collapsing the state.
Also of Q1, yes. So yeah, this is the main.
It's like a hidden bug in your program.
Yes, exactly. Yes, that's the point. Yes.
That's the reason
Yeah, it's similar. I mean, I think the things that is closer to this in classical computing can be like with the alias or the pointer, which you changing one pointer, but you're actually changing maybe some other. Yes.
So no more questions? Then let's thank Nicola.